Hello, this is Irene from Exam Help Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2, variant 1, October, November 2020. Question number 1, part A. Define the moment of a force about a point. So that's force multiplied by perpendicular distance. Part 2, determine the SI base units of the moment of a force. Moment is force into distance, where force is mass into acceleration and distance is meters. So the base unit for the moment of a force is kilograms meters squared per second square. Part B, a uniform rigid rod of length 2.4 meters is shown in figure 1.1. The rod has a weight of 5.2 newtons and is made of wood of density 790 kilograms per meter cube. Calculate the cross-sectional area in millimeters square of the rod. So density is mass divided by volume. The density of this wood is 790 is equals to mass is weight divided by 9.81 constant divided by the volume. Volume is cross-sectional area into length. So cross-sectional area into length of the rod is 2.4 meters. Hence area is 2.8 into 10 to the power of -4 meters square. To convert that to millimeters square, we'll multiply it with 1000 square. And we have 279.6 millimeters square of cross-sectional area of this rod. Part C, a fishing rod AB made from the rod in B is shown in figure 1.2. End A of the rod rests on the ground and a string is attached to the other end B. A support stick exerts a force perpendicular to the rod at point C. The weight of the rod acts at point D. The tension T in the string is in a direction perpendicular to the rod. The rod is in equilibrium and inclined at an angle of 56 degrees. The force and the distance along the rod of points A, B, C, and D are shown in figure 1.2. Part 1 shows that the component of the weight that is perpendicular to the rod is 4.3 newtons. So the vertical component of the rod's weight that is perpendicular to the rod is this one. Here we have angle 90 degrees and this angle is 56 degrees. So the vertical component of the rod's weight, or the component of the weight that is perpendicular to the rod, is 5.2 sine 56. This is equals to 4.3 newtons. Part 2, by taking moments about NA of the rod, calculate the tension T. So total clockwise moment about pivot A is going to be equal to total anti-clockwise moment about point A. The perpendicular force that rotates the rod clockwise is 4.6 newtons of force from support stick, and the perpendicular forces that rotate the rod anti-clockwise are rod weight's vertical component of 4.3 newtons, which is this one, and tension T. So total clockwise moment that is caused by 4.6 newtons of force multiplied by the perpendicular distance between the force 4.6 newtons and the pivot point A, which is 1.2 plus 0.6, that's 1.8 meters, is going to be equal to total anti-clockwise moment about same point A. So the first force that causes the rod to move anti-clockwise is tension T, and the perpendicular distance between tension T and pivot point A is 1.2 plus 0.6 and 0.6. So T into 2.4 meters of perpendicular distance, plus the other force that causes the rod to rotate anti-clockwise is the weight's vertical component, which is 4.3, and the perpendicular distance between 4.3 newtons of force and pivot point A is 1.2 meters. So 4.3 into 1.2 meters of distance, and that's how we get tension of 1.3 newtons. Part 2, a small block is lifted vertically upwards by a toy aircraft as illustrated in figure 2.1. As the block is moving upwards, the string breaks at t is equal to 0. The block initially continues moving upwards and then falls and hits the ground at time t is equal to 0.9 seconds. The variation with time t of the velocity v of the graph is shown in figure 2.2. A resistance is negligible. Part A state the feature of the graph in figure 2.2 that shows the block has a constant acceleration. So it's the constant gradient of figure 2.2 that shows the block moves with constant acceleration. So it's constant gradient. Part B, use figure 2.2 to determine the height of the block above the ground when the string breaks at time t is equals to 0. Okay, let's come back to figure 2.2. From t is equals to 0 to t is equals to 0.2 seconds, there is constant deceleration until speed is equals to 0, final speed is equals to 0, which tells that this part of the graph is the block's motion vertically upwards, because when it reaches its maximum heights, its final speed is going to be 0. It gets 0. So from t is equals to 0.2 seconds onwards till t is equals to 0.9 seconds, the ball falls, and this distance includes both parts, that is distance traveled after string breaks, that is at t is equals to 0 seconds, and height of the block above the ground when string breaks. This area can be represented with the help of this arrow, and this area is basically this much of distance. This is the part that we want, or the height of the block above the ground when the string breaks at time t is equals to 0. So we will subtract distances from t is equals to 0 to t is equals to 0.2 seconds, from t is equals to 0.2 seconds to t is equals to 0.9 seconds. Now, distance being covered by the block from t is equals to 0 to t is equals to 0.2 is area under the graph. So half into 0.2 into 1.96. And when it travels upwards, it travels a distance of 0.196 meters. And when it starts to travel downwards, it covers a distance of half into 0.7 into 6.86 of speed, and that's 2.401 meters. Thus, our answer is going to be the difference between these two distances, or we should say rather displacement, and that's 2.205 meters. Part C, the block has a weight of 0.86 newtons. Calculate the difference in gravitational potential energy of the block between time t is equals to 0 and time t is equals to 0.9 seconds. Here we'll be using the height from the previous part at time t is equals to 0 seconds. So difference in gravitational potential energy is m into g into h. M into g has a value of 0.86, and the difference in height is going to be 2.205 from the previous part, and hence the difference in gravitational potential energy of the block is 1.896 joules. Part D, on figure 2.3, sketch a line to show the variation of the distance moved by the block with time t. From t is equals to 0 to t is equals to 0.2 seconds. Numerical values are not required. So from t is equals to 0 to t is equals to 0.2 seconds, the block moves with constant deceleration. So in distance versus time graph, you represent this constant deceleration with a decreasing gradient graph. Part E, a block of greater mass is now released from the same height with the same upward velocity. Air resistance is still negligible. State and explain the effect, if any, of the increased mass on the speed with which the block hits the ground. So as long as air resistance is negligible, there is going to be no change to the motion of the block, because acceleration of free fall is unchanged for every mass. So no change or no effect on the speed, because acceleration of free fall is unchanged. Question number 3, part A, define force. That is mass into acceleration, where acceleration is final velocity minus initial velocity divided by time. So in terms of change in momentum, we are going to write that force is rate of change of momentum. Part B, a ball falls vertically downwards towards a horizontal floor and then rebounds along its original path as illustrated in figure 3.1. The ball reaches the floor with speed 3.8 meters per second. The ball is then in contact with the floor for a time of 0.081 seconds before leaving it with speed 1.7 meters per second. The mass of the ball is 0.062 kilograms. Calculate the loss of kinetic energy of the ball during the collision. So when the ball reaches the floor, it had a kinetic energy of half into 0.062 into its speed square, and that's 0.44764 joules of kinetic energy. And when it rebounds, it had a kinetic energy of half into 0.062 into 1.7 square, and that's 0.0896 joules of kinetic energy. So loss of kinetic energy is 0.44764 minus 0.0896, and that's 0.358 joules of loss of kinetic energy. Part 2, determine the magnitude of the change in momentum of the ball during the collision. So change in momentum is mass into final velocity minus initial velocity. Mass of the ball is 0.062. The final velocity is going to be 1.7, but we are going to include the sign since it's a vector quantity. Momentum is a vector quantity, and we must take signs into consideration, and the ball changes its direction, so it's going to be negative 1.7, and the change in momentum is going to be V minus mass into V minus Cu, so minus 3.8. 3.8 is going to carry a sign of positive, so change in momentum has a magnitude of 0.341 Newton seconds. Part 3 showed that the magnitude of the average resultant force acting on the ball during the correlation is 4.2 newtons. So average resultant force acting on the ball is its change in momentum divided by the time interval for that change in momentum. Change in momentum from the previous part is 0.341, and the time interval for which the ball is in contact with the floor is 0.081 seconds. So 0.081 seconds, and hence we have the magnitude of the average resultant force acting on the ball as 4.2 newtons. Part 4 used the information in Part 3 to calculate the magnitude of the average force of the floor on the ball during the collision. So average force of the floor is going to be equal to resultant force on the ball plus the ball's weight. So the resultant force acting on the ball due to the contact is 4.2 newtons, plus the ball's weight is going to be the mass of the ball multiplied by 9.81 of g, and hence we have the average force of the floor on the ball as 4.808 newtons. The average force of the ball on the floor during the collision, it's also going to be 4.808 newtons of force. It will be the same according to Newton's third law. Question number 4, part A, define for a wire stress. Stress is force divided by cross-sectional area. Strain is extension over original length of the wire. Part B1, a school experiment is performed on a metal wire to determine the Young modulus of the metal. A force is applied to one end of the wire with which is fixed at the other end. The variation of the force F with extension X of the wire is shown in figure 4.1. The maximum force applied to the wire is F1. The gradient of the graph line in figure 4.1 is G. The wire has initial length L and cross-sectional area A. Determine an expression in terms of A, G, and L for the Young modulus of the metal. So Young modulus is force into original length divided by cross-sectional area into extension. We have the gradient G in figure 4.1 as F by X. So F by X is equals to G. So in terms of A, G, and L, our Young modulus is going to be F over X, which is G, into L over A. Part 2, a student repeats the experiment in B part 1 using a new wire that has twice the diameter of the first wire. The initial length of the wire and the metal of the wire are unchanged. On figure 4.1, draw the graph line representing the new wire for the force increasing from F is equals to 0 to F is equals to F1. Young modulus is equals to FL by AX, where the gradient of figure 4.1 is F by X and cross-sectional area is A. When we take area to this side, we get the relationship between cross-sectional area and the gradient of the graph. So area is directly proportional to F by X, and F by X is also our gradient of figure 4.1. So cross-sectional area is directly proportional to gradient. When cross-sectional area increases by 2 times, the gradient, which is F by X, also increases by 4 times. So it's going to start from the same coordinate, that is the origin, and the graph will shift towards the left to increase the gradient, and it will end here. So we are going to have a straight line with an increased gradient. Part 3, another student repeats the original experiment in B Part 1, increasing the force beyond F1 to a new force, maximum force F2. The new graph obtained is shown in figure 4.2. On figure 4.2, shade an area that represents the work done to extend the wire from when the force is increased from F1 to F2. So work done is area under the graph. Work done to extend the wire from F1 to F2 is this part of the graph. Explain how the student can check that the elastic limit of the wire was not exceeded when force F2 was applied. So he can remove the force, and if the wire goes back to its original position, this confirms that it hasn't exceeded its elastic limit. So remove the force, and the wire goes back to its original length. Part 4, each student in the class performs the experiment in B Part 1. The teacher describes the values of the Young modulus calculated by the students as having high accuracy and low precision. Explain what is meant by low precision. So precision is closeness of Young modulus measurements in this question to each other. Young modulus with low precision means there is a large range of Young modulus values that students are getting. So you can write that low precision means there is a large range of values. Question number 5. A progressive wave wire passes at a point P. The variation with time of the displacement for the wave at P is shown in figure 5.1. The wave has a wavelength of 8 centimeters. Determine the speed of the wave. So speed is frequency into wavelength. Frequency where is 1 over time period. The time period for this wave is going to be from one crest to the other crest. So this is the time period for this wave, and it is 0.4 seconds. So speed is equals to lambda, which is wavelength, and it should be converted into meters. So this would be 0.08 meters. 0.08 divided by 0.4, this is equals to 0.2 meters per second of speed of the wave. Part B, a second wave Z has wavelength 8 centimeters and amplitude 2 millimeters at point P. Waves Y and Z have the same speed. For the waves at point P, calculate the ratio intensity of wave Z by intensity of wave Y. So intensity is directly proportional to amplitude squared. So amplitude of wave Z is 2 millimeters and that of wave Y is 4 millimeters. That is from the rest position to the maximum point, to the crest. So the intensity of Z is directly proportional to its amplitude squared, which is 2 squared, and amplitude and intensity of Y is directly proportional to its own amplitude squared, which is 4 squared. And hence the ratio of these two intensities is 0.25. Question number 6, part A, describe the conditions required for the two waves to be able to form a stationary wave. So the first one is that the incoming waves needs to be of the same speed and frequency. And the second condition would be that the waves there are going to be moving in the opposite directions and they must overlap to form a stationary wave. So incoming waves must travel in opposite directions. And overlap. Also, they need to be of same speed and frequency. Means they need to be in phase. Part B, a stationary wave on a string has nodes and antinodes. The distance between a node and an adjacent antinode is 6 centimeters. Say what is meant by a node. So that's a point where amplitude is 0. 0 amplitude. Part 2, calculate the wavelength of the two waves forming the stationary wave. So distance between a node and its adjacent antinode is always lambda by 4. That is a quarter of a wavelength. And that's 6 centimeters in this question. So 6 centimeters. That means that wavelength of the two waves that form the stationary wave is 24 centimeters. Part 3 states the phase difference between the particles at two adjacent antinodes of the stationary wave. So suppose this is the stationary wave that forms. These are the two antinodes. The phase difference between these two points is going to be of 180 degrees. Question number 7, part A, define the ohm. They are asking you to define not the resistance, but its unit ohm. So resistance is voltage divided by current. Hence, ohm is going to be equal to volt divided by ampere. Part B, a uniform wire has resistance 3.2 ohms. The wire has length 2.5 meters and is made from metal of resistivity 460 nano-ohm meter. Calculate the cross-sectional area of the wire. So resistance is equal to resistivity into length into cross-sectional area. Its cross-sectional area is equal to resistivity into length divided by resistance. The resistivity is in nano-ohm meter. We must convert that to ohm meter. So nano-ohm meter to meter is going to be multiplied by 10 to the power negative 9 into the length of the wire, which is 2.5 meters, and the resistance of the wire, which is 3.2 ohms. Hence, the cross-sectional area of the wire is 3.6 into 10 to the power of negative 7 meters square. Part C, a cell of EMF and internal resistance is connected to a variable resistor of resistance R, as shown in figure 7.1. The current in the circuit is I. Stated in terms of energy, Y, the potential difference across the variable resistor is less than the EMF of the cell. So this is due to some energy that is lost in the form of heat energy due to internal resistance of the battery. Some energy is dissipated, and that energy is called lost volts. Part 2, state an expression for E in terms of I, capital R, and small r. So we are going to follow Kirchhoff's second law over here, which is that total EMF in the loop is equal to total PD across the loop. This is the total EMF, and the PD across variable resistor R and the PD across the internal resistance will give us the EMF. So EMF is equal to total potential difference across variable resistor, which is I, multiplied by its resistance, plus the potential difference across internal resistance of the cell, that is I into small r. So this is IR plus I small r. Part 3, the resistance R of the variable resistor is changed so that it is equal to small r. Determine an expression in terms of only capital E and small r for the power P dissipated in the variable resistor. So power dissipation is equal to I square R. We have to remove the symbol I and bring R, small r, or capital E. So capital R is now equal to small r, as it is said right here that the resistance of the variable resistor is changed so that it is equal to small r. So we can write that current across the whole battery is equal to the EMF of the battery divided by the combined resistance of the loop, which is the sum of these two resistances, and since they are equal this time, so we can write 2R. So I in terms of capital E and small r is going to be E divided by 2R the whole square multiplied by small r. Hence the power dissipation in the variable resistor in terms of only E and R is going to be E square 4R. Question number 8, part A, state a similarity and a difference between a down quark and a down antiquark. So they share the same mass, but they have opposite charges. Part B, for a nucleus of aluminium 25, state the number of protons and the number of neutrons. So number of protons is equal to atomic number of the aluminium atom. That's 13, and number of neutrons is going to be the difference between the mass number and the proton number. That is 25 minus 13, which is 12. Part 2 show that the charge is 2.1 into 10 to the power of negative 18 coulombs. So number of protons is going to be equal to number of electrons in a neutral aluminium atom. So number of electrons are going to be 13 multiplied by the charge of a single electron, which is 1.6 into 10 to the power of negative 19. And that's how we get a combined charge on the aluminium's neutral atom. Part C, the nucleus in B is moved along a straight line from point A to point B in a uniform horizontal electric field in a vacuum as shown in figure 8.1. The electric field strength is 11 kilovolts per meter. Calculate the work done to move the charge from A to B. So work done is equal to force multiplied by the distance in the direction of force. Now force is equals to electric field strength into charge. Electric field strength is 11 kilovolts per meter. So we'll convert that to volts. So 11,000 into the charge of the aluminium atom from the previous part is 2.1 into 10 to the power of negative 18. Multiplied by the distance in the direction of force that it travels. Force that is going to be exerted on aluminium atom is going to be either towards the left or towards the right. It is moving towards the right, so distance in the direction of force is actually the 4 centimeters. So 4 centimeters must be converted into meters, that's 0.04. And hence the work done to move the charge from A to B is 9.24 into 10 to the power of negative 16 joules. So that was the end of the paper. Thank you for watching.